So the next problem is problem 78. I think I'm skipping problem 77, but it doesn't matter. So the question is, where does the normal line to the parabola y equals x minus x squared at the point 1, 0 intersect the parabola a second time? Illustrate with a sketch. I'm not going to illustrate this, but it's an interesting problem. So we have dy over dx is equal to 1 minus 2x. So we have f prime of 1 is equal to negative 1. Right? So the slope of our normal line is m is going to be equal to 1. So let's write down the equation. So we have y minus 0 is equal to 1 times x minus 1. Right? Right. So this is the equation of our normal line. So now we want to know, where does this normal line intersect this twice? So let's just make the y's equal each other. So I'm going to get x minus 1 is equal to x minus x squared. Take minus x from both sides, so I get negative 1 is equal to negative x squared, or 1 is equal to x squared, or x is equal to negative plus and minus 1. So the first time where we intersect is a plus 1. So the second time is a negative 1. So I believe we would probably have something like a graph that looks like that. We're going to have a line, and we're going to intersect like here and here, negative 1 and at 1. That's 1 and that's negative 1, something like that. Okay. Next problem. I'm going to do problem 80. Find equations of both lines to the point 2, negative 3. We're going to have two lines that are tangent to the parabola. Y is equal to x squared plus x. So we have f. So let's take f of x to equal this. F prime of x is going to equal to 2x plus 1. F prime of 2 is going to be 5. So that is the, what is that? The derivative. So that's the slope of our tangent line. So we're going to have fy plus 3 is equal to 5 x minus 2. Y is equal to 5x minus 5. So now, wait a second. Okay. So we want the slope of our second line to also be 5, because the slope of our first line is 5. So we want the slope of our second line. Oh wait. So in order to find the second line that passes through this and has the slope, right, we want this slope, we can take, what we can take is our points. So the points look in this form: x and x squared plus x. Any point on this graph, the x coordinate is x and the y coordinate is this. So in order, and then, so we're going to have so we're going to have x squared plus x minus 3, which is plus 3, divided by x minus 2. This is the slope between this line, this point, any arbitrary point, and this point. Well, we want this to be 2x plus 1, because we want the slope to be tangent to this, the slope passing through this and some arbitrary point. And this is going to help us find our x. So what we get is we get x squared plus x plus 3 is equal to x minus 2 times 2x plus 1 is equal to 2x squared plus x plus x minus 4x minus 2. So this is equal to 2x squared minus 3x minus 2. So let's get everything on one side. So we're going to get negative x squared. No, we could take a negative 2x from both sides. So we're so negative x squared and positive 3x, so plus 4x plus 5 is equal to 0, or in other words, negative 4 plus or minus the square root of 4 squared minus, so it's going to cancel, so plus 1 times, so 4 times 5 over negative 2. So this is going to give me negative 4 plus or minus, so this is 16 plus 20 is 36, so plus or minus 6 over negative 2, which is equal to, okay, so negative 4 plus 6. Negative 4 plus 6 is 2. So it's going to give me negative 1. And then negative 4 minus 6 is negative and 5. So we already found the 5, right? Here we have slope 5. So the other point is going to be negative 1, right? So for x equals negative 1 as a slope, as a point, and for x equals 5, the slope of our tangent line is going to be 5. And wait a second. No, sorry. So the first part I did about for all this is just simply incorrect because that the point, this is incorrect because that the point 2 and negative 3 does not lie on this function. Right, you plug in a 2 here, you don't get a negative 3, so I can't do this. I can't talk about the tangent at that point. But what you can do is you can find all the points, right? What we did do over here is correct. So we have our map, and we have a point which lies outside of the map, right? So this point is outside. And we want to find the two places which pass through this and are tangent to the graph. I didn't draw this correctly, but one would be something like that. The other doesn't exist, and well, now it exists. The other would go like that. So what you do is you take the equation between a given point and this point, and you set that equal to what you know you have as a slope, and then you solve and you'll find your 2 points that go through that point. And that's what we did. And so then for the next part of this problem, so we have the same equation, y equals x squared plus x, and we say, it says show that there is no line through the point 2 comma 7 that is tangent to the parabola. I'm not going to draw it, but so again you have f, so dy over dx is going to be 2x plus 1, and now we're going to have, and now every arbitrary point is again x comma x squared plus x. So again, finding the slope between this gives us x squared plus x minus 7 over x minus 2 is equal to 2x plus 1. Multiplying, so we get 2x plus 1 times x minus 2. Well, this gives us 2x squared minus 4x plus x minus 2. So this gives me 2x squared minus 3x plus 2. And we have that this is equal to x squared plus x minus 7 So now we get negative x squared plus 4x, and then 7 minus 2, I believe, is minus 9. It's going to be 0, right? You have negative 2, yeah. So obviously a real number will not exist to solve this equation, simply because that when you have your square root, so you're going to have your negative 4 plus or minus, and then when you have your square root, you're going to have, again, 4 squared, which is 16, and then you're going to have minus, and so you're going to have minus, and then 4 times 9, right? Because a is 1, and this is bigger than 16, right? So because of this, this is going to be negative inside your square root, and you're going to have a complex number, so you won't have real solutions to this problem. Okay, so now let's look at problem 1, which says use the product rule twice to prove that if f, g, and h are differentiable, then you have something. So I'm not going to do the second part, because the second part is kind of involves okay, I'll do the whole thing. I mean, this is proof, so the question really is, do I want to do this? But why not? So it might help. Okay, anyways, I have f, g, h prime, and I want to prove that this is equal to f prime g h plus f g h, and prime over here, plus f g h prime. So f g h prime, so we can think of this as a single function, and this is just going to be f g h prime plus h f g prime, right? And then let's just find this. So this is going to be, so this is equal to this, and this is equal to f g h prime plus h, and then times f g prime plus h g f prime by the product rule, and there we have it. This and that, they're the same exact thing. We just move around the functions a little, and we're multiplying them, so we can do that. So now if we take f equals g equals h, right, we want to prove that the derivative of f of x to the third power is equal to 3f of x squared times f prime of x. That's what we want to prove. So just take f equals g equals h over here. So we're going to have, so this is going to be f times f 3 times, and we're taking the derivative of it, and we get this, which is the same as saying f, right, f squared times f prime plus, again, this is f. So again, we have f squared times f prime, and again, this is f and that's f. So again, we have f squared times f prime. We take out the f prime, and we get is f. So we get is 3 f squared all times f prime, which is this, right? That's the same as 3f of x squared times f prime of x. That's the same as that. So that's proof. So now find the nth derivative of these two equations. So by taking a few derivatives and observing the pattern. So f of x equals x to the n, and we want to take fn of x. Well, so let's look at what happens. So f prime of x is n x n minus 1, and f double prime of x is n minus 1 x n minus 2. f triple prime of x is n minus 1, n minus 2, x to the n minus 3. If you do this n amount of times, so fn of x, what you're going to get is n factorial, right? N times n minus 1, oh sorry, this is 2, n minus 2, and then you're going to get over here n minus n, right? Because for 3 it's minus 3, for 2 it's minus 2. So I believe it's going to be x of z to the 0, which is just 1, and I think you're just going to get n factorial. Not sure. Okay. The next one is f of x is equal to 1 over x. So let's look at f prime of x. Well, that's going to give me negative 1 over x squared, right? Because it's going to be x times the derivative of 1, which is 0, minus 1 times the derivative of x, which is 1, all over x squared. That's what we get there. The second time, f double prime of x, we're going to get... So we're going to get 0 minus 2x, right, minus 2x over x to the 4th, which is going to be negative 2 over x to the 3. It's not going to be a negative, it's going to be a positive number at this point. And then 3 times for x, right, it's going to be positive because it's going to be x squared times 0 minus, and then minus 1 times 2x, and these minuses, and this is just going to be 2x, and then we're going to have over x to the 4th. And the next time we're going to get negative 2, right, we're going to get 0, and then negative 2 times 3x squared over x 6, which is going to give me negative 2 times 3 over x to the 4th power. And I think we can generally say that fn of x is probably going to be, so it's going to be negative 1 to the nth power. So let's see, so for 1 we have a negative, for 2 we don't, for 3 we do. Okay, so that looks right. Times n factorial, that looks right, over, and then we're going to have x n plus 1 down here. So that looks right. Why not? Okay, so the next problem, we are asked to find the second degree polynomial. So right, we want the highest, we want something in the form of, let's say p of x is equal to x squared. That's what we mean by second degree. Then we want a constant here plus bx plus c. And we want this such that p of 2 is equal to 5, p prime of 2 is equal to 3, and p double prime of 2 is equal to 2. And the best way to do it is to start down here because it will give us the least amount of conditions. So let's look at p prime of x. Well, that's going to give me 2ax plus b, and p prime of double prime of x is going to give me 2a, right? So, but we want this to be equal to 2. So in other words, we want a to be equal to 1. So we already started figuring out what p of x is. So p of x is going to be x squared plus, and let's figure out the rest. So now over here we know what 1 is, and what a is, it's just 1. So now this, we want this to be equal to 3. Or in other words, we want, what do we want? Oh, and this over here, right, the x is 2 over here now because we're plugging in a 2. Plugging in a 2. Over here we plugged in a 2, whatever. So now, so b is going to be also a 1. So we have plus x plus, and now c, Well, so now we have 4 plus 2 plus c is equal to 5, right? Because plugging in a 2 we get a 5. So we get c is equal to -1. So plus, so then minus 1. So that looks, let's see, p of 2 is 4 plus 2 minus 1, that's 5. P prime, I mean, looks fine on it. Okay, next problem. So the next problem involves differential equations, which are very, very important. So let's do it. So we want a y such that if we take the second derivative of y plus the first derivative of y minus 2y, we get x squared. That's the type of y that we want. So again, we want a y such as if you take the first derivative plus the second derivative minus 2 times without taking the derivative, you're just going to get x squared. And they're telling us that y equals ax squared plus b x plus c will, with certain constants, it will satisfy this equation. So let's find the constant. So let's just take what y, so y prime is going to be 2ax plus b, and y double prime is going to be 2a. So let's plug this in. So we're going to have, we want 2a, constants such as 2a, plus, and then this, so 2ax plus b, minus this, so that's going to be minus 2ax squared plus bx plus c. We want all this to equal to x squared. So c obviously has to be a 0 because we don't want constants, and probably, well, let's assume for a second that c equals 0. And let's also assume, okay, so now let's assume that b is equal to -2a. So this and this are going to cancel. And over here, and this, well, they're not going to cancel because the negative here. So that's not going to work. Get rid of the c. If we get rid of the a, if the b, so my screen shut down and I just came back in. Now the page that I was working on with the differential equations is gone, which I guess is actually a good thing because I didn't really know what to do with it. So let's just move on. So problem 85. You know what, I'll try the differential equations one because it is important. So again, y double prime plus y prime minus 2y is equal to x squared. And we have y is equal to ax squared. In the video, it should still have the part where I did all this. It's just that I don't have that page. So anyway, so y prime is equal to 2ax plus b, and y double prime is equal to it's equal to 2a. So now we're going to have 2a plus 2ax plus b minus 2, so let's put it in actually to not minus 2ax squared minus 2bx minus 2c is equal to x squared. So let's see. So if I make a to equal negative a half, if I make a to be negative a half, then this gives me what I want, which is the x squared. That's the only way to get that. So I need to make a to be negative a half. So let's start with that assumption. A is equal to negative a half. Well, now if a is equal to negative a half, then let's try to get this and this to cancel. Well, that would mean that b, so b is going to equal to a half, right? Yeah. So if b is equal to a half, so I have a half over here. Well, c, I have a half over here, and I have negative 1 over here. So I have negative 1 plus a half, so I still have a half. So c would have to be a half too. C would have to be a half. Let's see, let's plug this in. So I'm going to have negative 2 over 2 plus 2, so minus negative 2 over 2x plus a half minus, so then plus x squared minus just x, and then minus 1, yeah, minus 1. Okay, so I get a minus over here, but I also got a minus over here. That didn't work. Wait, let's try this with b being negative a half. Right, because this and this, these are not canceling, which way they were supposed to do. So I need b to also be, because this will be negative, and so this has to be, so b has to be negative a half. Then I'm going to have this, and then b is going to be negative over here. I'm going to have, so then c is going to have to be plus 3 over 2. 3 over 2. So let's see. So now this is going to be plus, right? Because b is negative a half. So this and this is going to cancel. And negative a half minus that, that's that. So this and this are going to cancel. I'm going to be left with x squared. Wow, I believe that's the answer. Okay, so now find the cubic function y equals ax to the third plus bx squared plus cx plus d, whose graph has horizontal tangent at the point negative 2 comma 6 and 2 comma 0, which means that m is 0. So we want y prime, which is equal to 3a x squared plus 2bx plus c. We want this to be equal to, so we want for negative 2, so we want 3a, a negative 2 is times 4 plus 2b, again negative 2, so this is going to be minus 4b plus c. This is going to be equal to 0. And another thing we want is a 2. So again, we're going to have 3a times 2. Now it's going to be plus 4b plus c to equal 0. So we want both of these. And because it's cubic, you cannot make a to be 0. That's sure. So let me see. So you can actually make b equals 0 because it will still keep it cubic. The a can't be 0, but the b can be, theoretically. And then you can make d whatever you want. And what you're going to need is sorry, this is 4. 3a times 4 is equal to negative c. Or in other words, so let's take c to, let's say, be 1. So c equals 1. So you're going to need this. Oh, wait. No, let's take a equals 1. A is going to be 1, so you're going to need c. You're going to need c to be negative 12. Yeah. Okay, next problem. I'm going to skip some of these. So now, a lot of the remaining problems are very similar to ones that we did with definitions of limits and, again, finding tangent lines. So I'm going to move on to the next section, which involves trigonometric functions. And we're going to now start doing that. Oh, and it's a small section, so hopefully I'll be able to finish it in 40 minutes or so. So first problem, this is on page 154. It asks if f of x is equal to, let me see, 3x squared minus 2 cosine x. 3x squared minus 2 cosine x. We want to find f prime of f. So that's going to be 6x minus 2 times the derivative of cosine, which is negative sine. So negative sine of x. Just remember the derivatives for trigonometric functions. It's important. Or in other words, we get 6x plus 2 sine x. So for the next problem, we have f of x is equal to sine x plus a half cotangent. I'm always going to do everything in terms of either sine, cosine, or tangent, and just write down the definitions for this. I'm not actually going to use the derivatives for cotangent, for example, because it's better to just, I think, just remember 3 of the functions, sine, cosine, and tangent, and then just use the definitions for sine, cosine, and tangent. So now we get cosine x, and then using the quotient rule, we're going to have plus, and then we're going to have a negative, right, because it will be tangent times the derivative of 1, which is 0, so minus 1 times the derivative of 2 tangent, which is 2 secant squared x over 2 tangent x squared. that's that. Now let's look next problem. Oh, I'm just doing the odd ones. Let's go to the even ones. F of x is equal to the square root of x times sine of x. So f prime of x is going to be the square root of x times cosine of x plus sine of x times a half x to the negative a half, right by the product rule. So now problem 4 gives us y is equal to 2 so I'm just going to write out based on the definition 1 over sine x plus 5 cosine x. So y prime is going to be, so we're going to have a negative 2 cosine x over sine x squared, right? And you can again use the definitions for tangent and cosecant to show how this is the same as the derivatives given in the chapter, which it is. Like this is how they came up with this. Anyways, plus, so minus 5 sine x, because the derivative of cosine is negative sine. So next problem is problem 5. So we're given, I believe it's problem 5 anyways, g of t is equal to 3 t to the third cosine t. So g prime of t is going to be t to the third negative sine t plus cosine t 3t squared. Next problem 6, g of t is equal to 4 1 over cosine t 4 plus tangent t. So g prime of t is equal to cosine, so negative 4 times negative sine, so just sine of x, over cosine, t squared plus secant squared of t. Next problem is problem 7, h5 or whatever. I'm going to change it because I should know, but I don't actually currently remember the name for that. Angle. Okay. So h of x is equal to x cosecant, so that is sine over sine x minus 1 over tangent x. Right, yeah. So h prime of x is going to be, again, quotient rule. So we're going to have sine of x minus x times cosine x over sine x squared minus, and then you're going to have a minus over here, and then you're going to have a secant squared x over tan of x squared. Okay, next problem. So we have y is equal to ua cosine u plus b cotangent u. So y prime is equal, these are u's, so it's equal to u times the derivative of this, which is negative a sine u plus, and this is k, cotangent 1 over tangent u. So this is going to be negative 1 secant squared of x over tangent u squared plus, and now you just write this part, so a cosine u plus b cotangent times u, which is 1. So that is the derivative for that. The next part is y. Put in place y is equal to x over 2 negative tan x. So y prime is equal to 2 negative tan x times 1 minus x. 2 is 0, and then I get negative secant squared x for the tan x over 2 minus tan x squared. Problem, we have y is equal to 1 plus sine x over x plus cosine x. So y prime is going to be x plus cosine x times the derivative over here, which is cosine x, minus 1 plus sine x times the derivative over here, which is 1 plus minus sine x, all over x plus cosine x squared. Next problem, f of x is equal to secant x over 1 plus secant x. In other words, it's equal to 1 over cosine x over 1 plus 1 over cosine x. Okay, so this is equal to 1 over cosine x over cosine x plus 1 over cosine x, finding the common denominator, and this is equal to cosine x over cosine x times cosine times cosine x plus 1. So now we can take the derivative of this. So f prime of x is going to be equal to cosine x times cosine x plus 1 times the derivative of cosine x, which is negative sine x, minus cosine x times the derivative of this, which we're going to use the product rule. So you're going to have cosine x times the derivative of this, which is negative sine x, plus cosine x plus 1 times the derivative of this, which is negative sine x, all of this over cosine x times cosine x plus 1 squared. Ouch. Okay. So now problem 12 gives us y is equal to 1 plus secant x over tan x, which is equal to 1 plus cosine x, 1 plus 1 over cosine x over tan x. This is equal to cosine x plus 1 over cosine x all over tan x, and this is going to be equal, again, a over b divided by c over d is equal to a d over bc. So over here, we imagine this is over 1. You get cosine x plus 1 times 1 over cosine x tan x. Taking the derivative now of that, we get that this is equal to cosine x times, cosine x times tangent x times negative sine x minus cosine x plus 1 times the derivative of this, which is cosine x secant squared x plus tan x negative sine x all over cosine x tan x squared. Okay, next problem. Y is equal to sine of x over x squared. Y prime is equal to x squared cosine x minus sine x 2x over x to the 4th power. Next problem we have is y is equal to 1 over sine x times x plus 1 over tangent x. We have y prime is equal, we have the product rule over here, so 1 over sine x times 1 plus, and then I'm going to have negative secant squared x over tan x squared plus x plus 1 over tan x times, and then I'm going to have negative cosine x over sine x squared. Okay, next problem is y is equal to secant x tan x. So y prime by the product rule. I'm not going to have a secant here. I'm going to have a 1 over cosine x. So y prime is going to be equal to, well, we can think of this as just some quotient. So cosine x secant squared x minus tan x negative sine x over cosine x squared. Okay. Finally, y is equal to x squared sine x tan x. Okay, a bunch of product rules. The first one we're going to do is going to be x squared times sine x times secant squared x plus, if you remember, we proved that fhg prime is equal to fhg prime plus fh prime g plus f prime g hg. So we're just going to use that, so plus, then we're going to have x squared cosine x tangent x plus 2x sine x tangent x. But just following the product rule, you get that too, right? You're going to have this times the derivative of that. Now you still have to take the derivative of this. So you're going to have plus, and taking the derivative of this. So you have that, taking the derivative of this, you get, so now you have to take the product rule here, so you get that, but plus, because now you took the derivative of sine x, but now you have to take the derivative of x squared, so you end up with that. Okay, so let's do one of these, but because of how I have been doing this, all of these should be pretty simple. We want to, so we have f of x is equal to cosecant x, and we want to prove that f prime of x is equal to negative cosecant x times cotangent x, and I'm going to use the formulas for sine, cosine, and tangent to do this. So we have this is equal to 1 over sine x. So f prime of x is going to be negative 1 times cosine x over sine x squared, which is equal to negative, and then you're going to take a tangent x out of the cosine and one of the sine x's, and then you're going to just, so now you're going to have one more sine x on the bottom. That's going to give you cosecant x. And we just proved, oh right, because you have cosine on top and sine on the bottom, so you don't have tangent, you have cotangent. Because you have, right, tangent is x. Let me write this more clearly. Tangent x is equal to sine x over cosine x. Cotangent is equal to 1 over tangent x, which is equal to 1 over sine x over cosine x, which is the same as 1 over 1 over sine x over cosine x, which is equal to, by the rule I just mentioned, a over b over c over d is equal to a d over bc. This becomes cosine x over sine x. So cotangent is the same as cosine x over sine x. Okay, so the other proofs do the same thing. So now let's do problem 21. I'm going let's see, I'm gonna do this for 15 more minutes, I guess, and then I'm gonna start a new video, but not tonight. Y equals secant x. We want to find the equation of the tangent line to the curve pi over 3 comma 2. So y prime is going to give us, so this is 1 over cosine, 1 over cosine x. So now we're going to get negative 1 times negative sine, so that's sine over cosine x squared, which is the same as tangent x times secant x, which is one of the proofs. So that this also, this is 18, problem 18, that secant squared, secant, its derivative is this. Anyway, so now we plug in a pi over 3. So we get tan pi over 3 times secant pi over 3. This is equal to m. And I am not going to actually, I don't know, all these pi's over there. I mean, plug it into a computer or something. I don't remember this stuff anymore. But anyway, m is and then you find the equation of the line for the points pi, for the point pi over 3 comma 2. Let's just do problem 24, skip a little, 24. Y is equal to 1 over sine x plus cosine x, right? And we want to find the equation for 0, 1. Y prime is going to be sine at -1 cosine x minus sine x, that's the derivative of the bottom, over sine x plus cosine x squared. Plug in a 0, so this becomes -1 times 1 minus 0, right? Cosine of 0 is 1, sine of 0 is 0. That, at least, you should remember. And then sine of 0 is 0 plus cos, so this is going to be 1. So this is going to be -1. And then, so we have y minus 1 is equal to -1x, or y is equal to -x plus 1. That's the equation of the line. So I am going to skip a little. Let's look at problem 31. So we're asked first to use the quotient rule to find the derivative for f of x is equal to tan x minus 1 over secant x. First use the quotient rule, then simplify this expression using sines and cosines and see if we get the same result. So using the quotient rule, we get secant x times secant squared x, right? Yeah, minus tan x minus 1 times, what's the derivative of secant x? So we have 1 over, I'm just going to look at that, secant x tan x, and all this over secant x squared. So this, and one of these cancel. Okay, so the answer is secant squared x minus tan squared x minus tan x over secant x. The other part, we have tan of x is sine of x over cosine x minus 1, and this is over 1 over cosine x. So this is equal to sine of x minus cosine x over cosine x. And then what we do is we multiply this by cosine x, right, because we're flipping it. These cancel, and what we get for our derivative is cosine x plus sine x. Cosine x plus sine x. So is this cosine x plus sine x? Let's write that there, cosine x plus sine x. I don't know. Let's see, let's try to simplify this a little if we can. See what happens. So that is equal to 1 over cosine x squared minus sine of x squared over cosine x squared minus, oh wait, there, no, oh no, yeah, 2 is up there, sine x over cosine x. So let's add a cosine x. So this is going to be cosine x. Now this is cosine x squared. So on top, what we get is 1 minus sine 2x minus sine x cosine x. And then the bottom, so we're going to just multiply all this by cosine x, because in the bottom we have 1 over cosine, which it just flips to up here. And now what we get is cosine x minus sine 2x x squared cosine x minus sine x cosine squared x. And now I don't know what to do. Take a sine. It's not going to work. Okay. I don't know. Anyway, some simplifications of that might help. Next problem I'm going to do is problem 33. For what values of x does the graph f of x equals x plus 2 sine of x have horizontal tangent? So we take f prime of x is equal to 1 plus 2 cosine x, and we set this to 0, which means we have 2 cosine x is equal to negative 1. Let's not look at the half. Actually, yeah, so we want cosine x to equals to a negative a half. And I don't know where cosine does that. So we cannot continue that problem. So the next problem, problem 35, I'm skipping problem 34 because there's probably a similar problematic situation that will arise. But for the next problem, problem 35, a mass in a spring vibrates horizontally on a smooth level surface. Its equation of motion is given by x of t. So it's vibrating, it's going back and forth. But you have a mass, and it's just jumping back and forth. And it's given in terms of xt is equal to 8 sine of t. So the position it is over time is given through that. So find the velocity and acceleration. So we're going to do the same thing that we did before with the particle. This is the velocity. It's going to be 8 cosine t. And the acceleration is going to be negative 8 sine t. Find the position, velocity, acceleration of the mass at time t equals 2 pi over 3. Well, we just plug it in. We get 8 sine 2 pi over 3, 8 cosine 2 pi over 3, and negative 8 sine 2 pi over 3. Okay, so this is going to be the last problem for today. I'm gonna basically continue in this section in the next video.